In the depths of a squash court beneath the University of Chicago's football stadium, something happened on the 2nd of December, 1942, that forever changed the course of human history. There, in a makeshift laboratory made of graphite bricks, uranium, and wooden timbers, a group of scientists watched anxiously as a series of control rods were slowly withdrawn from a strange structure known as Chicago Pile 1. The man at the center of this groundbreaking moment was Enrico Fermi, a quiet, intense physicist who combined theory with experimentation like few others ever had. With the final rod removed, the pile became self-sustaining. A controlled nuclear chain reaction, something previously confined to imagination, was now a reality. Fermi turned to his colleague and whispered, "The reaction is self-sustaining. The pile is going critical." The world had entered the atomic age, and Enrico Fermi had opened the door. But who was this man? A Nobel Prize-winning physicist from Italy, a refugee from fascism, a contributor to the development of the atomic bomb, a genius in both mathematical theory and experimental design, a master teacher whose students would go on to win more Nobel Prizes than most universities could boast. He was also deeply human, pragmatic, funny in a quiet way, sometimes socially awkward, always driven by logic. He could estimate the energy of an atomic explosion by watching a paper fall. He created the framework for statistical mechanics that now bears his name, Fermi-Dirac statistics. He built the first nuclear reactor with his own hands, and yet he also wrestled with the moral consequences of what his discoveries enabled. Enrico Fermi was not just a physicist. He was a bridge between worlds, theory and experiment, Europe and America, peace and war. He was a man who could make the invisible visible, who could turn pure thought into physical power. This is the story of Enrico Fermi, the man who made the atom speak. Chapter 1. Birth in Rome, Genius in the Making, a Child of Rome. Enrico Fermi was born on the 29th of September, 1901, in Rome, Italy, a city where the ruins of ancient empires stood beside the chimes of Catholic bells. He was the third child of Alberto Fermi, a railroad inspector, and Ida de Gaddis, a schoolteacher. The Fermi household was strict but supportive of education, especially as Ida recognized her youngest son's thirst for knowledge early on. Enrico showed signs of brilliance as a child. At just 10 years old, he was devouring physics books and solving mathematical puzzles that would baffle most teenagers. He wasn't an outgoing child, but he was fiercely curious, often disappearing for hours with a book in his lap or a homemade experiment bubbling in the corner of the family apartment. Tragedy would shape him early. At age 14, Enrico's beloved older brother Giulio died during a routine throat operation. Devastated but determined, Enrico dove deeper into his studies, perhaps finding solace in the unchanging laws of physics, while the chaos of emotion and mortality swirled around him. The marketplace of ideas. In 1918, at the age of 17, Enrico Fermi entered the Scuola Normale Superiore in Pisa, one of Italy's most prestigious schools. He had scored near-perfect marks on the entrance exam, astonishing his evaluators with a treatise on the physics of sound that would have been ambitious for a doctoral student. In Pisa, he was left to his own devices, a perfect environment for someone so intellectually independent. Fermi thrived on self-teaching. He read German journals, devoured Einstein's papers, and debated the nature of matter with anyone who would listen or just with himself. His time in Pisa also revealed a second truth about Fermi. He was as much an experimentalist as a theorist. Many of his peers focused on theoretical calculations, but Fermi was known to build his own apparatus, often from scratch, conducting his own experiments and testing the theories he read about. This rare duality would become his trademark. Theoretical precision, practical genius. By the time Fermi was in his early 22nd, He had written papers on general relativity, quantum mechanics, and statistical physics. He began corresponding with leading physicists across Europe and gained recognition quickly, especially for his ability to distill complex problems into solvable ones. Fermi's unique mind could switch between broad theory and specific application in seconds. He once remarked, "Before I came to the laboratory, I could understand the whole universe. Now I can't find a screw for my experiment." But that humility masked his brilliance. It was in these years that he developed what would become Fermi-Dirac statistics, a mathematical framework that described how particles called fermions, later named after him, behaved. The young professor. In 1926, at the astonishing age of 24, Enrico Fermi was appointed professor of theoretical physics at the University of Rome, the youngest full professor in Italy at the time. There, he began to assemble what would later be called the Via Panisperna Boys, a group of brilliant young physicists including Edoardo Amaldi, Emilio Segre, Franco Rossetti, and Ettore Majorana. Their headquarters was a small laboratory on Via Panisperna, a quiet street in Rome. From this humble place, groundbreaking experiments on neutron bombardment, beta decay, and nuclear fission would emerge. But more on that later. Fermi's reputation was growing internationally. In 1927, he was invited to the Solvay Conference, where he met luminaries like Niels Bohr, Max Planck, and Albert Einstein. He stood as their equal despite being decades younger. A marriage of minds. In 1928, Fermi married Laura Capone, a woman from a prominent Jewish family. Intelligent, supportive, and politically aware, Laura would become a vital pillar in Fermi's life, not just as a partner, but as a bridge to the world beyond science. Their union also foreshadowed dark times ahead, as Italy drifted deeper into fascism. They had 2 children, Nella and Giulio, named in memory of Fermi's lost brother. At home, Fermi was a devoted father and loved to hike, swim, and play chess. His genius didn't isolate him from daily life, it simply accompanied him. Chapter 2. Early Education and the Road to Physics. An early spark of genius. Enrico Fermi's intellectual fire ignited long before formal education gave it structure. Born into a modest Roman household, his earliest lessons came not from classrooms, but from curiosity. He would take apart clocks, radios, and mechanical toys just to understand how they worked and sometimes put them back together better than before. In his teens, a fateful encounter pushed his scientific hunger to new heights. A family friend, a physics professor named Adolfo Amedei, took notice of Enrico's abilities. Amedei gifted him 2 crucial texts, Elementorum Physicae Mathematicae by Father Andrea Carafa, and Treatise on Theoretical Physics by Augusto Righi. These books were not meant for a child, but Enrico devoured them with ease. Amedei would later recall, he had the soul of a physicist before he even knew what a physicist was. Self-taught and fearless. By 17, Enrico had read all available physics texts in Italian. Dissatisfied, he turned to German and English sources, teaching himself the languages as he went. He read Maxwell, Planck, and Einstein in their original words. While many students struggled with high school algebra, Fermi was solving partial differential equations and studying tensor calculus. What made Fermi different wasn't just his intellect. It was his practical logic. He didn't memorize, he understood. If a theory didn't make intuitive sense, he wouldn't move forward until it did. His style was crisp, clean, and deeply grounded in reality. In a way, Fermi was creating his own curriculum, one that merged the abstract elegance of mathematics with the tangible results of physical experimentation. The Scuola Normale Superiore in Pisa. At 17, Fermi applied to one of the most elite institutions in Italy, the Scuola Normale Superiore in Pisa. The school accepted only the best, those who passed a grueling entrance exam in mathematics and physics. Fermi didn't just pass, he astonished the professors. His exam essay on the motion of sound waves was so advanced that it left no doubt. This was a prodigy. At Pisa, Enrico encountered freedom, and he used it to its fullest. He shunned lectures, preferring to study on his own. Professors, rather than disciplining him, gave him space. He began doing independent research projects, exploring thermodynamics, wave mechanics, and electron behavior. He also started making a name for himself by publishing scientific papers as a teenager. One early paper dealt with general relativity, a field still being shaped by Einstein himself. Theoretical rigor meets experimental ingenuity. While many of his classmates focused on theory, Fermi began building simple instruments to test what he read. He believed that the best theory was worthless without experiment, a belief that would become the foundation of his future success. In the school basement, he assembled rudimentary laboratory equipment. He measured radiation using photographic plates. He studied gas behavior by constructing makeshift vacuum tubes. Pisa didn't have a large physics lab, but with a few wires, tubes, and mirrors, Fermi made one. By the time he graduated in 1922, Fermi had become known throughout Italy's academic circles. He had earned not just degrees, but a reputation as a physicist of the future. Rising star in post-WWI Italy, post-war Italy was politically unstable, but intellectually vibrant. Physics was undergoing a revolution, quantum mechanics was emerging in Germany, and Einstein's relativity was challenging Newtonian orthodoxy. Fermi found himself swept into these new waves of thought. He traveled briefly to Göttingen and Leiden, meeting Max Born, Paul Ehrenfest, and others at the heart of the quantum upheaval. While there, he also began to understand something critical. Europe's theoretical physics was soaring, but its experimental base was lagging, especially in Italy. When he returned, he made it his mission to change that. Fermi-Dirac statistics, a new order of matter. In 1926, Fermi introduced a breakthrough that would define him. The Fermi-Dirac statistics, developed independently and simultaneously by Paul Dirac in England. The problem at hand was how particles with half-integer spin, such as electrons, behave when crowded into the same energy system. Classical statistics, like those used by Maxwell Boltzmann, failed to explain observed behaviors in metals and gases. Fermi's solution? A new set of rules. No two identical fermions can occupy the same quantum state simultaneously, an idea consistent with Pauli's exclusion principle, but extended into the statistical realm. Fermi's work not only explained the electronic structure of atoms, but also laid the foundation for semiconductor physics, solid-state electronics, white dwarf and neutron star behavior, quantum theory of heat capacity. Einstein, who reviewed Fermi's paper, praised it as a monumental advance. Without Fermi-Dirac statistics, modern physics and electronics would be unthinkable. Returned to Rome, the professor of a new era. In 1926, Fermi was appointed professor of theoretical physics at the University of Rome, the youngest in Italy's history. At just 25, he began attracting brilliant young minds to his lab on Via Panisperna. This group, later dubbed the Via Panisperna Boys, included names that would echo through science: Franco Rossetti, Emilio Segre, Edoardo Amaldi, Bruno Pontecorvo, Ettore Majorana. With this team, Fermi conducted pioneering experiments in neutron physics, radioactivity, and nuclear transmutation. They discovered, for instance, that slow neutrons were more effective in causing nuclear reactions, a revelation that would ultimately lead to controlled fission. Their lab was poor in funding, but rich in intellectual firepower. Their tools were simple, but their minds were sharp. Fermi taught by doing. Students recalled how he would begin from first principles, derive the equations, and then build the experiment all in one afternoon. He was methodical, clear, and utterly logical. More than a professor, he became a mentor and a magnet for young talent. Enrico Fermi was a self-taught genius who mastered advanced physics before entering university. At Pisa, he distinguished himself as both a theorist and a practical experimenter. He introduced Fermi-Dirac statistics, a cornerstone of quantum mechanics. As the youngest professor in Italy, he gathered the Via Panisperna boys, creating a hub of nuclear research in Rome. Chapter 3: Breakthroughs in Quantum Mechanics and Statistics. A mind that danced between atoms. By the early 1932nd, Enrico Fermi had already earned a reputation as one of Europe's most brilliant physicists. But he was just getting started. While Fermi was renowned for Fermi-Dirac statistics, he was not content resting on his theoretical laurels. The world of radioactivity, especially beta decay, captivated his imagination. Physicists had observed that in some radioactive decays, energy appeared to vanish. According to the laws of conservation, this couldn't be. Enter Fermi. The mystery of beta decay. Beta decay occurs when an atomic nucleus emits an electron, but in the 1922nd and early 32nd, this process puzzled scientists. The energy of the emitted electron varied and didn't always add up with the parent atom's mass energy. Something was missing. Niels Bohr even considered the radical idea that energy conservation might not hold at the subatomic level. Fermi disagreed. He took a bolder, more elegant approach. What if an invisible particle carried away the missing energy? Inspired by Wolfgang Pauli's earlier suggestion of a neutron, later clarified as the neutrino, Fermi proposed a fully fleshed-out quantum field theory of beta decay in 1933. In a paper he modestly titled Tentativo di una teoria dell'emissione dei raggi beta, an attempt at a theory of beta radiation, Fermi described a process where a neutron turns into a proton, an electron is emitted, a new particle, the neutrino, is released, carrying away energy and momentum. This theory was revolutionary. It was the first successful application of quantum field theory to weak nuclear interactions, a precursor to the electroweak theory of the Standard Model. Rejected, then revered, Fermi's paper was initially rejected by the prestigious journal Nature for being too speculative. But when it was published in Zeitschrift für Physik, it was instantly recognized by his peers as a stroke of genius. Decades later, his theory would be experimentally confirmed, and neutrinos would become a foundational part of particle physics. But Fermi was already looking forward to what atoms might do when bombarded with neutrons. The neutron, a tool of transformation. After James Chadwick's discovery of the neutron in 1932, physicists realized they had a powerful new probe. Neutrons, unlike protons or alpha particles, were uncharged and could penetrate deep into atomic nuclei. Fermi and his Via Panisperna team took up the challenge. They built a neutron gun using beryllium and polonium and began systematically bombarding elements across the periodic table. Their experiments were methodical, one element at a time, careful measurements of resulting isotopes and radioactive decay. And then came a startling discovery: the power of slow neutrons. In 1934, Fermi noticed that when they slowed down the neutrons by passing them through paraffin wax or water, their ability to induce nuclear reactions dramatically increased. Why? Slower neutrons spent more time near atomic nuclei, increasing the chance of interaction. This insight would prove crucial to nuclear energy and weapons. It was a key step toward chain reactions and the design of nuclear reactors. Fermi had discovered how to manipulate the fundamental building blocks of matter, not just describe them. Transmutation and the threshold of fission. As they moved down the periodic table, Fermi's group bombarded uranium and thought they were creating new transuranic elements. In truth, they were unknowingly causing nuclear fission, splitting the uranium nucleus into lighter elements, releasing massive energy. It would take the work of Lise Meitner, Otto Hahn, and Fritz Strassmann to interpret this correctly in 1938, but Fermi had come dangerously close to discovering fission first. Had he paused to analyze the mysterious radioactive byproducts of uranium, Fermi might have changed the world 4 years earlier. Yet his modesty and drive to move forward kept him from dwelling on what could have been. The Nobel Prize. In 1938, Fermi was awarded the Nobel Prize in Physics for his demonstrations of the existence of new radioactive elements produced by neutron irradiation and for his related discovery of nuclear reactions brought about by slow neutrons. He traveled to Stockholm with his wife, Laura, for the ceremony, but their journey didn't end there. The rise of fascism and a fateful decision. By the late 1932, Italy had aligned with Nazi Germany, and Mussolini had passed a series of anti-Semitic laws. Fermi's wife, Laura, was Jewish, and their children would be subject to discrimination and danger. Despite his fame, Fermi knew the writing was on the wall. So, after receiving the Nobel Prize, he did not return to Italy. Instead, the Fermi family quietly sailed to New York City, beginning a new chapter and helping change the destiny of the world. Fermi developed the first complete theory of beta decay, predicting the neutrino. He discovered the enhanced effects of slow neutrons, paving the way for controlled nuclear reactions. He nearly discovered nuclear fission before the Germans. In 1938, he was awarded the Nobel Prize in Physics. He used the Nobel ceremony as a pretext to escape fascist Italy, emigrating to the United States with his family. Chapter 4. The Discovery of Neutron Moderation and the Race to the Reactor. Arrival in America, a New World. When the SS Franconia docked in New York Harbor on the 2nd of January, 1939, Enrico Fermi and his family disembarked quietly. Few around them realized that one of the greatest minds of the 20th century had just fled Europe. Fermi wasn't just seeking safety, he was seeking freedom, both intellectual and political. Almost immediately, Fermi was offered a position at Columbia University in New York City. The American physics community had already admired his work from afar. Now they had him in person. And just in time, because less than 3 weeks later, the world learned a word that would forever alter the course of human history: fission. News from Germany: the birth of nuclear fission. On the 26th of January, 1939, a scientific lecture at George Washington University, delivered by Niels Bohr and Lise Meitner, revealed the truth behind uranium experiments in Germany. Otto Hahn and Fritz Strassmann had split the uranium atom. Fermi had unknowingly done the same in Rome 5 years earlier, but hadn't realized it. Now the implications were clear. If atoms could be split and release energy, and if that splitting could be chained, then it was theoretically possible to create an explosion of unprecedented power, or, alternatively, a source of controlled energy. The Chicago Group takes shape. As tensions rose in Europe and rumors of a world war grew louder, the U.S. government became interested in atomic energy, and no one had more experience in manipulating neutrons than Fermi. In 1942, Fermi relocated to the University of Chicago, where a secret group of scientists assembled under the code name Metallurgical Laboratory, or MET-Lab for short. Their task: to prove that a controlled, self-sustaining nuclear chain reaction was possible. Fermi's brilliance was instrumental. He wasn't just a theorist calculating probabilities. He was building, testing, leading. His style was systematic, logical, and precise. If the chain reaction could be achieved, Fermi would find the way. Constructing the Chicago pile, the experimental design was bold and almost primitive by modern standards. Location: a disused racquetball court under Stagg Field, the university's football stadium. Materials: graphite blocks to slow down neutrons, uranium pellets as the fuel, wooden timbers and cadmium rods for control, a manual crank system to insert and withdraw control rods. Fermi called the structure the Chicago Pile 1, the first nuclear reactor. It resembled a giant beehive or an ancient ziggurat. The risk was unimaginable. No one had ever attempted such a feat. Would the chain reaction spin out of control? Would it explode? But Fermi was calm. Colleagues later said he understood the physics so well, he never once lost confidence. The 2nd of December, 1942, the world changes. At 3:25 p.m. on the 2nd of December, 1942, Fermi gave the final instructions. The team withdrew the final cadmium control rod. Instrumentation confirmed what Fermi already suspected. A self-sustaining nuclear chain reaction had begun. The reaction would double in power every few minutes. The scientists exchanged tense glances. Fermi was calm, calculating, his slide rule in hand. After 28 minutes, he ordered the control rods reinserted, stopping the reaction. A code was phoned to Washington. The Italian navigator has landed in the New World. It was the first time humans had released nuclear energy in a controlled manner. Civilization had entered a new era, the atomic age. Fermi had become the first man in history to both theoretically describe and experimentally demonstrate the power of the atom. Why Fermi succeeded where others failed. There were many brilliant physicists at the time: Bohr, Einstein, Oppenheimer. But Fermi had something rare. He combined the mathematician's mind with the engineer's hands. He could design, build, test, and verify all on his own. While others wrote equations on blackboards, Fermi was in the lab stacking uranium blocks and aligning counters. He also had a gift for estimation. He could make fast, intuitive guesses called Fermi problems that helped him quickly evaluate complex scenarios. For example, how many piano tuners are there in Chicago? How much energy was released by the atomic bomb dropped on Hiroshima? This style of rough but reasonable calculation became legendary and is still taught in physics classes today. Scaling up. Toward the bomb. With the success of CP-1, Fermi's next mission was scaling the technology for wartime use. The military now fully invested relocated operations to Los Alamos, New Mexico. Fermi moved again, becoming a key figure in the top-secret Manhattan Project. But the memory of that squash court experiment never left him. Years later, he would reflect, before the 2nd of December, 1942, we had the theory. After it, we had the power. Fermi arrived in the U.S. just as the discovery of nuclear fission shocked the scientific world. At the University of Chicago, he led the creation of Chicago Pile 1, the world's first nuclear reactor. On the 2nd of December, 1942, he achieved the first controlled nuclear chain reaction, proving that atoms could be harnessed safely. Fermi became the father of neutron moderation, a discovery that made both nuclear energy and the atomic bomb possible. Chapter 5. A Secret War. The Manhattan Project and Fermi's Ethical Dilemma. To the Desert. Los Alamos begins. By early 1943, the scientific world was split between those who fled Europe and those who feared Hitler would build the bomb first. The United States government, recognizing the threat, poured resources into what became the Manhattan Project, the largest scientific and military collaboration in history. In a remote corner of New Mexico, on a windswept mesa, a secret lab rose out of the sand. Los Alamos Laboratory. Behind high fences and guarded gates, hundreds of the world's top physicists, chemists, and engineers gathered to do the unthinkable: build an atomic bomb. At the center of this effort was Enrico Fermi. He was appointed Associate Director under J. Robert Oppenheimer and placed in charge of reactor development and weapon physics. While Oppenheimer was the charismatic leader, Fermi was the technical anchor, the person others came to when answers were needed and risks had to be calculated. He was nicknamed the Pope because he was infallible. Engineering, the unimaginable. Fermi's role involved solving some of the hardest technical problems the project faced. Designing the reactors that would produce plutonium at Hanford, Washington. Modeling neutron behavior inside bombs to optimize yield. Testing and improving critical mass calculations, how much uranium or plutonium was needed for a chain reaction. Helping resolve engineering challenges with bomb detonation, compression, and safety. He was everywhere, checking blueprints, running simulations, leading experiments, and mentoring younger scientists. Many said that when Fermi entered a room, the tone changed. Discussions became more focused, more rational. He had a gift for making the complex simple and for making science move forward, even in a fog of uncertainty. Fermi's calculations, the mind behind the blast. One of Fermi's most famous moments came not in a lab, but in the desert sands of New Mexico. On the 16th of July, 1945, the world's first atomic bomb was detonated at the Trinity test site. Scientists gathered several miles from ground zero, protected only by goggles and flimsy shelters. As the countdown ticked down and the detonation boomed across the desert, Fermi performed a simple experiment. He dropped pieces of paper into the air and watched how far the shock wave carried them. From this crude yet elegant measurement, he estimated the bomb's explosive yield to be about 10 kilotons, a figure that turned out to be astonishingly accurate. The final yield was 1820 kilotons. This became a classic Fermi estimate, a reminder of how far sharp logic and intuition could go, even in the shadow of history's most devastating weapon. Victory and the bombings of Hiroshima and Nagasaki. Less than a month after the Trinity test, the bombs were used. The 6th of August, 1945, Hiroshima. The 9th of August, 1945, Nagasaki. Fermi watched the news with quiet dread. He had known intellectually that the bombs would work. But seeing their effects, tens of thousands dead, cities leveled, shadows burned into concrete, was something else entirely. He had helped build the weapon. He had in some way helped end World War II, but at what cost? Fermi did not make public statements like Oppenheimer. He was not given to poetry or regret, but those who knew him said he changed in those weeks. He became more subdued, more cautious. He had witnessed the power of science unbound, and it humbled even him. Fermi and the ethics of the bomb. While Fermi wasn't known for emotional reflection, he did express moral concerns. He supported the Frank Report, a document written by Manhattan Project scientists urging the U.S. to demonstrate the bomb before using it on civilians. The government ignored it. Fermi later said privately that he felt torn. He had helped build a weapon of mass destruction, but if Hitler had gotten there first, the consequences could have been unthinkable. His wife Laura wrote in her memoir, "Enrico was a man of logic, not emotion, but even he could not look away from what he had helped create. In a world now armed with atomic fire, the boundaries of physics had moved, and Fermi stood at the center of a moral storm he could not fully contain. Recognition and return." After the war, Fermi received numerous awards, including the Medal for Merit, the highest civilian award in the U.S. military, appointment to the General Advisory Committee of the Atomic Energy Commission, where he advised on nuclear policy, a return to the University of Chicago, where he resumed teaching and research. But he would never again be simply a scientist. He had become a symbol of brilliance, of responsibility, of the dual-edged sword that is scientific power. Fermi was a central figure in the Manhattan Project, second only to Oppenheimer in influence. He solved key problems in reactor design, bomb physics, and neutron modeling. He personally estimated the Trinity test yield using only a falling piece of paper, an iconic moment in scientific history. Fermi was haunted, though quietly, by the use of the atomic bomb on civilians. After the war, he turned toward teaching and advising, forever changed by what he had helped unleash. Chapter 6. The Atomic Prophet, Fermi After the War. Back to Chicago, the professor returns. In the autumn of 1945, as the world reeled from the horror and relief that followed the war's end, Enrico Fermi quietly returned to teaching at the University of Chicago, specifically at the Institute for Nuclear Studies. But he was no longer simply a scientist. He was now a living legend, known across the globe as the man who had built the first nuclear reactor and helped unleash the atom's power. Still, in true Fermi fashion, he remained humble. He didn't boast, he didn't demand privilege, he went back to what he loved most, thinking, experimenting, and teaching. A scientist in his element, Fermi didn't slow down. Over the next decade, he continued to make seminal contributions in multiple areas of physics. 1. Cosmic rays and particle physics. Fermi turned his attention to high-energy cosmic rays and helped shape the new field of particle physics. He developed a theory, now called Fermi acceleration, explaining how cosmic rays gain energy as they travel through space and interact with magnetic fields. This helped lay the groundwork for understanding high-energy astrophysical phenomena, a foundation for modern astrophysics. 2. The birth of quantum electrodynamics, QED. Fermi's post-war work overlapped with the rise of quantum electrodynamics, the theory that describes how light and matter interact. While not a founder of QED, Fermi's clarity and precision helped students and colleagues grasp its deeply abstract nature. His lectures, later compiled as notes on quantum mechanics and nuclear physics, became standard references in the field. 3. Nuclear physics and pion theory. Fermi also explored the strong nuclear force and engaged in discussions surrounding the role of pions, mesons, as force carriers in the nucleus. He supported early efforts to build particle accelerators that could test these theories, work that later evolved into the research done at Fermilab, named in his honor. The great teacher, while his wartime efforts changed history, Fermi's post-war teaching may be his most enduring legacy. He had an uncanny ability to explain complex physics in simple terms. Students and colleagues marveled at his lucid, logical explanations and his resistance to mathematical showmanship. He taught physics as an art of clarity. Many of his students went on to become giants of 20th century science, including Murray Gell-Mann, Nobel laureate and developer of the quark model; Chen-Ning Yang and Tsung-Dao Lee, Nobel laureates for parity violation; Jack Steinberger, Nobel laureate for neutrino beam methods; Owen Chamberlain, co-discoverer of the antiproton; Walter Zinn, reactor designer and first director of Argonne National Laboratory. These students often called themselves Fermians, proud heirs to the logic and discipline Fermi taught. The Fermi problem approach. Beyond lectures, Fermi had a signature way of thinking through problems. He believed that any physical question, no matter how complex, could be broken down into rough, estimable quantities. His classic Fermi problems included: how many piano tuners are there in Chicago? How many molecules of Julius Caesar's last breath are in the air you just inhaled? What's the energy released from a small nuclear reaction? The value wasn't in precise answers, it was in estimating orders of magnitude, developing a feel for the physics. Today, Fermi estimation is taught in physics, engineering, and even consulting firms. It encourages creative reasoning, grounded in logic, a perfect reflection of Fermi's mindset. Science and the public. Fermi wasn't political, but he wasn't silent either. As a member of the General Advisory Committee of the Atomic Energy Commission, He participated in post-war policy discussions. In 1949, he opposed the development of the hydrogen bomb, a bomb many times more powerful than the one dropped on Hiroshima. He joined a group of scientists, including J. Robert Oppenheimer, arguing that the H-bomb was militarily unnecessary and morally dangerous. But their opposition was overruled. Despite this, Fermi's role on the committee allowed him to shape nuclear policy with a voice of reason, one grounded in both technical expertise and quiet moral concern. The beginning of Fermilab, in the 1952nd, discussions began about building a massive particle accelerator outside Chicago. Though Fermi wouldn't live to see it completed, his vision guided its creation. In 1967, 13 years after his death, the Fermi National Accelerator Laboratory, Fermilab, was named in his honor. It became one of the world's leading centers for high-energy particle physics, where scientists would later discover the bottom quark, neutrino oscillations, and explore the Higgs field. It was a fitting tribute, a lab dedicated to exploring the smallest building blocks of the universe, just as Fermi had done his entire life. Fermi returned to academia as a towering educator and researcher. He contributed to cosmic ray theory, QED, and nuclear structure. He mentored a generation of students, many of whom became Nobel laureates. He developed the now famous Fermi problem approach, blending creativity with calculation. He quietly advised against the hydrogen bomb, advocating for scientific responsibility. Chapter 7: Illness, Legacy, and the End of an Era. Time slows for the master. By the early 1952nd, Enrico Fermi was still a force in physics. He lectured regularly at the University of Chicago, traveled for international conferences, and advised on high-level scientific policy. But beneath his steady presence, something was wrong. In 1953, Fermi began experiencing persistent abdominal pain, fatigue, and weight loss. At first, he dismissed the symptoms. It wasn't in his nature to complain. But eventually, the pain worsened. Doctors delivered a crushing diagnosis: stomach cancer, the same disease that had claimed his father. Fermi, then only 51 years old, knew the prognosis was grim. Even in decline, he worked. Despite the pain, Fermi refused to withdraw from science. He continued to meet with students, publish papers, and work on nuclear models. His final scientific contributions included deep insights into pion-nucleon interactions and critiques of emerging theories in elementary particle physics. One colleague noted, "Even when his body weakened, his mind remained sharper than anyone else's in the room." Fermi also took time to organize his thoughts for posterity. He prepared and revised lectures, wrote final letters to colleagues, and met with the physicists who would inherit the field he had helped create. Final lectures, final lessons. In 1954, knowing his time was limited, Fermi delivered his final series of public lectures at the University of Chicago. These talks were packed with young scientists, eager to learn from a man who had touched nearly every corner of modern physics. His voice had grown softer, but his mind remained precise. He concluded one lecture with the remark, "One should not underestimate the power of simple assumptions." It was, in many ways, his final teaching to think clearly, question deeply, and simplify without compromise. A quiet passing. On the 28th of November, 1954, Enrico Fermi died at his home in Chicago, surrounded by his wife Laura and their children. He was only 53 years old. The world mourned the loss of one of the greatest physicists of all time. Tributes poured in from around the globe. Albert Einstein called him a physicist of rare insight. Niels Bohr remembered him as a master of both intuition and reason. The New York Times published a front-page obituary titled, "Enrico Fermi, Builder of the Atom Age, Dies." Yet Fermi would have probably shrugged off the attention. He never sought fame. He never chased headlines. His legacy was not in celebrity, but in truth and clarity. Legacy set in stone. Fermi's impact spans disciplines and generations. His name now graces fermions, the category of particles that obey the Pauli exclusion principle. Fermi energy, Fermi level, and Fermi surface. Cornerstones of quantum and solid-state physics. Fermilab, one of the world's premier particle accelerators. Fermi Gamma Ray Space Telescope, an orbiting observatory studying black holes, neutron stars, and dark matter. Element 100, Fermium, FM, a synthetic element named in his honor. Fermi Paradox, his famous question on extraterrestrial life. If the universe is so old and vast, where is everybody? But his greatest legacy may lie in his students, the minds he shaped, who went on to redefine physics, cosmology, and chemistry. Generations of scientists credit Fermi not just with teaching them science, but teaching them how to think. Laura Fermi's memoir. After his death, Fermi's widow, Laura Fermi, published a moving memoir titled Atoms in the Family. In it, she painted a personal portrait of the man behind the equations, a loving husband and father who swam daily and cracked quiet jokes, a man who never raised his voice and kept no enemies, a rationalist who believed deeply in democracy, education, and the search for truth. Her book became a bestseller, offering a rare glimpse into the humanity behind the physics, a life that changed the world. Enrico Fermi lived only 53 years, but in that time he founded the field of quantum statistics, predicted the neutrino, discovered the importance of slow neutrons, built the first nuclear reactor, helped develop the atomic bomb, educated a generation of future Nobel laureates, inspired a global framework for scientific reasoning. He once told a student, "If you cannot explain it simply, you don't understand it." By that measure, no one understood modern physics better than Enrico Fermi. Fermi was diagnosed with terminal stomach cancer in 1953. He continued working until the end, contributing to nuclear theory and mentoring students. He died quietly in 1954, leaving behind a scientific and educational legacy unmatched in modern history. His name is immortalized in physics, concepts, scientific facilities, and even the periodic table. His greatest gift was the power of simplification and clarity in science. Chapter 8. The Mind of Fermi. Style, Thought, and Philosophy of Science. A mind like no other. Enrico Fermi didn't just do science, he redefined how scientists thought about problems. His mind was a unique blend of mathematical rigor, experimental craftsmanship, and clear logic. Unlike many brilliant scientists who got lost in abstraction, Fermi remained anchored in simplicity. He once said, "There are two kinds of truth: the trivial truth, where the opposite is clearly false, and the profound truth, where the opposite is also true." This duality of truth reflected Fermi's approach, always searching for clarity, even in ambiguity. Theory meets experiment. Fermi stood out as one of the very few physicists in history who was equally skilled in theory and experiment. Most great physicists fall into one of two camps: theorists, who devise abstract equations and models; experimentalists, who build instruments and run tests. Fermi was both. He could derive complex statistical formulas in the morning, then calibrate a neutron detector in the afternoon. He didn't just propose the idea of slowing neutrons, he built the apparatus to test it himself. When students brought equations to him, he'd often reply, "Let's go measure it." His colleagues compared him to a Renaissance master, someone who could design, build, and refine from vision to execution. Fermi's problem-solving philosophy. Fermi's genius wasn't just in getting the right answers, it was in asking the right questions. He pioneered a form of thinking that's now taught in engineering and physics courses worldwide: the Fermi estimate. What is a Fermi problem? A Fermi problem is a question that seems impossible to answer precisely, but can be approximated with logic and basic knowledge. For example, How many piano tuners are there in Chicago? How many cells are in the human body? How much energy is in a bolt of lightning? Fermi didn't care about perfection. He cared about reasonability. His philosophy was, even a wildly imprecise estimate is better than no estimate at all. This approach trained scientists to break big problems into small parts, use dimensional analysis and order of magnitude thinking, avoid paralysis by uncertainty. Today, Fermi estimation is a key skill taught in physics, finance, logistics, AI, and even consulting. It represents Fermi's broader philosophy, science as structured intuition. A compass for simplicity. Fermi believed that the best scientific ideas were simple, testable, elegant. He distrusted overcomplication. When a student showed him a derivation that spanned multiple pages, Fermi would challenge them. Is there a simpler way? His lectures were short, clear, and full of physical insight. He used as few variables as possible. He emphasized physical meaning over mathematical formalism. Students learned that science wasn't about writing the longest equation, it was about grasping the core principles. Build, test, refine, Fermi's experimental ethos. In the lab, Fermi was hands-on. He could solder circuits, adjust vacuum tubes, and modify detectors himself. He didn't rely on lab technicians, he often worked beside them. He believed experiments should be repeatable, cheap, and transparent. One famous story tells of a complex neutron counting machine that malfunctioned. While others debated repairs, Fermi quietly reached over, tapped a valve, and said, "There, fixed." It wasn't magic. It was experience, patience, and attentiveness. He often told students, "A good scientist must also be a good plumber." The teacher's teacher, though he won the Nobel Prize and advised presidents, Fermi was most proud of his role as a teacher. His classes were legendary. He rarely used notes. He'd walk in, ask a question, and build a lesson from the ground up. Students said he made the hard things seem easy and the easy things beautiful. He mentored dozens of scientists who later won Nobel Prizes and led key discoveries in particle physics, cosmology, quantum field theory, reactor design. But Fermi didn't just teach facts. He taught a way of thinking, one that balanced logic with curiosity, simplicity with depth. His views on scientific culture. Fermi believed science should be collaborative, not competitive, global, not nationalistic, grounded in reality, not ideology. Though he worked on the atomic bomb, he never saw science as a political weapon. He once warned, "Science is not good or bad. It is a tool. The morality lies in its use." He was wary of dogma in all forms, be it political, religious, or academic. He encouraged skepticism, reason, and humility. He despised scientific pretension. He valued clarity over prestige, and was known to challenge even famous physicists if their logic didn't hold. Fermi's intellectual compass. At the heart of Fermi's mind was a quiet but powerful philosophy. Know the first principles. Break problems into steps. Measure when possible. Estimate when necessary. Build before you debate. Never stop learning. These principles, simple as they may seem, made him a towering intellect in the age of complexity. Fermi pioneered a unique style of logical estimation and simplicity in scientific thinking. He was one of the rare scientists who mastered both theory and experiment at the highest level. His Fermi problems became a model for how to approach uncertainty logically. He taught science not just as information, but as a mindset. His belief in clarity, intuition, and hands-on work shaped generations of physicists and thinkers. Chapter 9. Global Influence. How Fermi Shaped Modern Science. The Reach of a Single Mind. When Enrico Fermi passed away in 1954, he left behind more than publications, prizes, or reactors. He left behind a global blueprint, a model of how science could be done, how it could be taught, and how it should be handled responsibly. His impact was not limited to the United States. From Europe to Asia, from government think tanks to satellite observatories in space, the imprint of Fermi's work spans continents and disciplines. Physics worldwide, Fermi's disciples and scientific institutions. Across the post-war world, countries seeking to develop nuclear energy or physics research modeled their programs after the framework Fermi had helped build. Hess, Italy, the rebirth of Italian physics. After World War II, Italy's scientific reputation had collapsed under the weight of fascism. But Fermi's reputation and his former colleagues, like Edoardo Amaldi and Emilio Segre, revitalized the country's research institutions. Amaldi helped found CERN, the European Organization for Nuclear Research, following Fermi's example of international cooperation. Japan and the rise of reactor science. Japanese scientists studied Fermi's reactor models to design civilian nuclear programs after the war. Fermi's concept of slow neutron moderation became the gold standard in nuclear energy worldwide. TT, the USSR and the race for the bomb. Soviet physicists studied translated versions of Fermi's works, though on the opposite side of the Cold War, many Soviet nuclear physicists privately admired his clarity. Even in secrecy, his reactor, mathematics, and neutron diffusion equations helped fuel Soviet atomic development. India's peaceful nuclear program. Indian physicist Homi Bhabha, often called the father of India's nuclear program, referred to Fermi's work when designing India's early reactors. Fermi's writings helped define the technical groundwork for peaceful applications of nuclear technology in developing nations. Into space. Fermi and astrophysics. Even though he died before the space age began in earnest, Fermi's ideas helped shape the physics of the cosmos. Fermi acceleration. His 1949 theory of cosmic ray acceleration described how particles gain energy from shock waves in space, like those from supernovae or galactic magnetic fields. This theory became foundational in astrophysics and space radiation studies. Fermi paradox. In 1950, during lunch with colleagues at Los Alamos, Fermi asked a now famous question: if the universe is teeming with life, where is everybody? This became the Fermi paradox, the puzzle of why, in a vast and ancient universe, we haven't yet encountered extraterrestrial intelligence. This single question launched the search for extraterrestrial life, SETI. New theories of galactic communication, evolution, and civilizational collapse. Philosophical discussions about humanity's place in the cosmos. Fermi Gamma Ray Space Telescope. Launched in 2008, NASA named its cutting-edge space observatory the Fermi Gamma Ray Space Telescope. It scans the sky for the highest energy radiation, detecting pulsars, quasars, and gamma ray bursts, fulfilling Fermi's vision of seeing into the invisible. Fermi's legacy in education. In universities across the world, Fermi's textbooks, lectures, and techniques continue to shape the way physics is taught. Textbooks and course notes. His lectures on nuclear physics and notes on quantum mechanics are still used in advanced courses. His simple problem-solving style is taught as the gold standard for students entering theoretical and applied physics. The Fermi School of Thinking. Schools like MIT, Caltech, and Cambridge all have professors who were either directly taught by Fermi or shaped by his students. His legacy spawned a culture of science built on clarity, logic, and experimental validation, ethics, and scientific responsibility. Even as his name became synonymous with nuclear power, Fermi carried with him a strong internal sense of responsibility. He was not a political activist, but he believed scientists should inform policymakers with truth and clarity, warn of dangerous consequences, even if unpopular, uphold science as a global, collaborative endeavor. Atomic ethics. Fermi's opposition to the hydrogen bomb stemmed from concern, not naivete. He believed that once a weapon existed, it would be used, but that didn't absolve scientists from warning the world. Global science. Fermi strongly supported international collaboration long before it became fashionable. He urged young scientists to share knowledge freely, regardless of nationality or ideology. Awards, honors, and namesakes. Enrico Fermi's name has been honored around the globe. Fermilab, premier particle physics facility in the United States. Fermium, FM, element 100-inch the periodic table. Fermi Telescope, a cutting-edge space observatory. Fermi Problems, a formal teaching method worldwide. Fermi National Award, one of the highest U.S. honors in science. Streets, schools, and research centers around the world bear his name from Rome to Chicago to Tokyo. Even fictional stories and sci-fi films reference the Fermi paradox as a central existential theme. Fermi's influence extended far beyond his lifetime and beyond physics. Nuclear programs, scientific collaborations, and education systems across continents were shaped by his work. His questions, like the Fermi paradox, sparked entire fields of inquiry. His theories, such as cosmic ray acceleration, expanded our understanding of space. His name lives on in institutions, elements, awards, and space telescopes. His ethical approach to science remains a model for scientists facing powerful and dangerous discoveries. Chapter 10. Fermi's Enduring Image. Portrait of a Scientific Hero. The man behind the numbers. Enrico Fermi was often described as calm, methodical, and modest. But those words don't capture the quiet gravity he carried, a man who could hold the secrets of the universe in his mind and still explain them with the simplicity of a chalk sketch. He was not flamboyant like Richard Feynman, nor eccentric like Einstein. He was not confrontational, political, or charismatic in the traditional sense. Fermi's presence was rooted in intellectual integrity. To those around him, he was simply the most balanced mind in physics. Demeanor in daily life. Fermi lived simply. At the University of Chicago, he walked to work, carried his own lunch, and dressed modestly. He preferred sweaters over suits and was more likely to be found tinkering in a lab than speaking at elite banquets. He enjoyed swimming almost daily, even in cold Chicago weather, hiking especially in the Alps and American West, chess and logic puzzles, though he often beat his opponents too easily, conversations with students more than social gatherings with dignitaries. He spoke with a slight Italian accent, smiled often, and was known for short bursts of dry humor. He once told a student struggling with a quantum mechanics problem, "Either your math is wrong or the universe is." Family life. Fermi was devoted to his wife, Laura Capon, and their two children, Giulio and Nella. He shielded them from the pressures of war, politics, and fame as best he could. Despite his global influence, Fermi never let his work override his role as a father. Laura often described him as a man with a powerful mind and a quiet heart. In the evenings, he often played cards with his children or sat reading in his favorite armchair, lost in thought but never too distant. Among peers, respected and revered. At conferences, Fermi was treated with unusual reverence. Niels Bohr said, "Fermi was not just a physicist, he was physics itself." Colleagues who clashed with each other, like Oppenheimer and Teller, both admired Fermi, often seeking his opinion as a neutral compass. He could challenge theories without ego, disagree without offense, and resolve tensions with clarity. During the Manhattan Project, he became the go-to man for unanswerable questions. If a bomb design failed, if an experiment stalled, if a moral line was crossed, Fermi was consulted. The cult of Fermi. After his death, a unique phenomenon emerged, a quiet hero worship, not just for what Fermi did, but how he did it. Former students formed what some called the cult of Fermi, not a religious devotion, but an intellectual one. They told stories like his legendary paper toss estimate at the Trinity bomb test, his tendency to simplify complex math into a single, meaningful diagram, how he could sense when an equation or result just felt right. In classrooms worldwide, physics instructors began asking, what would Fermi do? He became not just a physicist, but a symbol of clear thought, practical reasoning, and scientific humility. Quotes that define a mind. Fermi left behind many quiet but profound sayings. Never confuse elegance for truth. It is no good to try to be clever. All that is necessary is to be right. Whatever nature has in store for mankind, unpleasant as it may be, men must accept, for ignorance is never better than knowledge. He distrusted cleverness without substance. He revered truth even when it was painful. To Fermi, science was not a contest, it was a compass. Fermi and the human condition. While Fermi rarely spoke in poetic terms, his life told a story of balance. Between power and restraint, between logic and compassion, between theoretical curiosity and moral responsibility, he knew that the knowledge he uncovered had helped split atoms and cities alike. He never claimed to have all the answers. He simply believed it was his duty to ask better questions and to do so honestly. Fermi in cultural memory. Today, Enrico Fermi is remembered not only in physics, but in philosophy seminars, especially regarding the Fermi paradox, engineering classes where Fermi problems are now a standard tool, public policy discussions about nuclear ethics, documentaries, biographies, and global museums, space exploration missions, science education curricula across dozens of languages. His name has become synonymous with clarity, precision, and modest genius, and yet he never sought any of this. In fact, he once joked to a colleague, "It is better to be wrong simply than complicatedly." Fermi was deeply respected for his humility, clarity, and simplicity. He lived modestly, valued family, and avoided public attention. Among scientists, he became a moral and intellectual compass, a quiet giant. His sayings, methods, and examples continue to guide teaching and thinking today. He remains an enduring figure of what science can and should be: logical, ethical, and honest. The voice of the atom. Why Fermi still matters today. A legacy woven into the universe. It has been decades since Enrico Fermi walked the halls of the University of Chicago, dropped a scrap of paper into the Trinity blast wave, or stood quietly in front of a chalkboard to explain quantum decay, but his presence is still felt in every nuclear reactor, every physics lecture, every estimate done on the back of a napkin. He is not just part of history, he is part of how we think. In a digital age, the Fermi mindset endures. In the 21st century, computers simulate what Fermi once calculated by hand. Machine learning predicts physical systems that Fermi might have estimated in his head. Artificial intelligence writes summaries of quantum mechanics, but Fermi, without any of these tools, could sketch the same conclusions using logic, chalk, and intuition. And yet, his style has never been more relevant. In a world of complexity, Fermi taught clarity. In a sea of information, Fermi taught reduction. In an era of precision, Fermi taught the value of a first-order guess. Engineers at SpaceX, data scientists at Google, physicists at CERN, they all use Fermi's reasoning style today. His methods have outlasted Cold Wars, governments, and technological shifts. The Fermi paradox in the age of space exploration. Perhaps the most philosophical contribution Fermi made is the question that still haunts thinkers today. Where is everybody? The Fermi paradox is now the cornerstone of astrobiology, SETI, Search for Extraterrestrial Intelligence, and the ethics of artificial intelligence. It asks why, in a universe that should teem with intelligent life, we seem to be alone. This question opens doors not only to astronomy, but to human psychology. evolutionary biology, ethics and philosophy, the existential future of our species. In this sense, Fermi didn't just study particles, he studied our place in the universe. From atoms to AI, a voice of logic. In modern quantum computing, researchers manipulate fermions, particles governed by the very statistics Fermi helped define. In artificial intelligence, engineers borrow Fermi-style problem-solving, build a simple model, estimate the bounds, refine it. Even the global conversation around nuclear energy and weapons policy still leans on his insights. How much uranium is needed for a bomb? How can you safely moderate a nuclear chain reaction? How do you balance knowledge with morality? Fermi's life reminds us that science is not a thing, it is a way of thinking. The eternal student, Fermi once said, "Whatever nature has in store for mankind, unpleasant as it may be, men must accept, for ignorance is never better than knowledge." This belief that truth, however uncomfortable, is better than false certainty, remains the core of all honest science. He never sought to predict everything. He sought to understand the parts he could, to illuminate the path forward. He was, to the very end, a student of nature. Why Fermi still inspires. Fermi's influence endures because he represents an ideal that transcends time. He wasn't motivated by power or recognition. He didn't seek to be radical or revolutionary. He was motivated by truth, precision, and humble mastery. He showed the world how to build a bomb but warn against its use, design a reactor but insist on safety, teach Nobel laureates but still make time for undergraduates, ask about aliens not as science fiction but as a serious philosophical puzzle. He taught us to think deeply, clearly, and responsibly. Closing words, the atom speaks, and so does the mind. In the final analysis, Enrico Fermi was not just a man of atoms, he was a man of principle, patience, and practicality, a builder of systems, a seeker of truth, a teacher of minds. He never courted celebrity, but he became the quiet conscience of a nuclear world. And when asked to summarize his life's work, he would not list his papers or his patents. Instead, he would likely say, "I just tried to understand things clearly." That simple statement may be the most powerful legacy of all.